Minkowski's spacetime does not describe the true shape of reality, and exactly as in the title. Observing the world around us, we have the impression that we live in a spacetime described by the Minkowski model. But looking at the sky, we have the impression that the sun is moving across the sky. Both statements are false, because observations give us a false picture of reality. Both the motions of the sun in the sky and the motions of the surrounding bodies simply look different than they actually do. According to my model, which I hope will soon become yours, reality is four-dimensional and Euclidean. It's the same as we see every day, only with one more dimension. In this four-dimensional space, there are bodies that are actually waves. In the case of uniform and rectilinear motions, and I will deal with these motions in this presentation, these wave bodies move along rectilinear trajectories with an absolute velocity equal to unity. They interpret the motion along their trajectories as the flow of time, and the length of the trajectory traveled is a measure of the time that elapsed in a given body coordinate system. The trajectories in E4 bodies interpret as the axis of time of their coordinate systems. Thus, trajectories of wave bodies will be denoted by the letters t, t1, etc. These bodies send and receive interactions in three directions perpendicular to their trajectories in four-dimensional Euclidean space. Since the bodies communicate only through interactions, so they can only observe each other along the directions in E4 into which the observed bodies send interactions. These directions are perpendicular to the trajectory of the observed body, so are different for different observed bodies. And now, let one body, let's call it T, observe two other bodies, T1 and T2, moving along different trajectories. Observing the motions of the bodies along the directions of propagation of the interactions, the observer measures the distance from the first body as x1 according to the direction in which body T1 sends interactions, and the distance from the second body as x2 according to the direction in which body T2 sends interactions. So the observer measures distances from different bodies along different directions in E4, but there are no reference points in space other than those body waves the observer is observing, so the observer does not know that these directions can be different. And in the Euclidean model, it is a description of the real observational process. However, we see this process differently. We live in a world where it uses three mutually perpendicular space dimensions to describe reality. We have also known for some time that time is the fourth dimension, so it has also automatically and without any proof been assumed that the time dimension is perpendicular to the other three dimensions. So the observer, in order to represent this observation in such a coordinate system as he knows, draws a vertical time axis and a horizontal spatial axis. And on such a diagram he puts down two distances x1 and x2, and since he is not able to determine that, in fact, in four-dimensional space these directions are different, so he plots both distances along the same spatial direction. And so the Minkowski spacetime is created. And how does the fact that actually the directions x1 and x2 are different manifest itself? It manifests itself by the presence of relativistic effects. Note that in the Euclidean space proposed here, the description of relativistic effects is trivially simple, and a high school student or even the final grades of primary school should have no problem with it. Take, for example, the observation of a body T1 by an observer T. It can be seen that the time dilation and the limitation of the velocity of bodies to the value of 1, here the speed of light, follows immediately from simple trigonometric relations for the right-angled triangle formed by the trajectories of the observer and the observed body, and the direction perpendicular to the trajectory of the observed body, along which we measure the distance from that body. What is difficult here? Meanwhile, the description of the same phenomena in Minkowski spacetime requires covariant notation, the principle of conservation of the spacetime interval, of the Lorentz transformation, and a long study after which you already know everything but understand nothing. In the figure showing the same observation of two bodies in Minkowski spacetime, it can be seen that the time axis of the systems in motion must be on a different scale to the observer's time axis. Change in scale of the time axis of systems in motion is determined by the hyperbolas seen in the figure. Meanwhile, really, the dimensions in real Euclidean space do not change. We simply observe the trajectories of different bodies along different directions in Euclidean space, and hence the impression of a change of scale of the time axis. So, Minkowski spacetime describes reality as we see it, whereas the Euclidean space model describes reality as it really is. Conclusion: the Minkowski spacetime does not show the true picture of reality. Of course, a lot of doubts may arise after such a trivial presentation. The answers can be found in my other presentations on my YouTube channel or in article on ResearchGate.net, Chaos.com and my website EuclideanReality.com. There will also be new presentations. If you are interested, please subscribe to my channel. Thank you for your attention.